So let's start with liquids. Well, we already know a lot about liquids. Because we essentially did a whole section on solutions and molarity and concentration. So there isn't much left to talk about liquids, but I just want to briefly mention two properties that liquids have. And this is the liquid's viscosity. I'm totally spelling this wrong. So viscosity is, so we have viscosity, we have capillary forces, and we have cohesion. And we have adhesion. So these are the primary properties or properties that liquids have. And I'm pretty sure you've all heard of these different properties before, at least in some manner, and you may actually understand some of these properties a little bit. So the first is viscosity. And viscosity is essentially of how essentially the liquids flow against one another. So a measure, how should I put this? A measure of how easily a liquid flows against itself. So you could think about, for instance, honey would have high viscosity. And something like ethanol low viscosity. And essentially the ways we look at how viscosity are influenced are essentially the size of the molecule, the shape of the molecule, the temperature, and the intermolecular forces between the molecules. So these are all factors which influence viscosity. So that's really all I want to say about viscosity. I only wanted to really touch on it from our conceptual points. So I'm pretty sure you've all heard of and are at least familiar with viscosity before, yes? You guys hear what I said? I said, are you guys all, you've all pretty much heard of viscosity before, right? Or I assume you've all heard of viscosity before, and this explanation makes sense. Yeah, it's essentially just a measure of how easily a fluid flows against itself. And if you think about it, if we increase the temperature, the viscosity will go down. So it makes sense, because if you increase the temperature, you're going to increase the rate at which the molecules are vibrating. And because of that vibration, you are going to allow the molecules to slide past one another more easily. Size obviously matters, because if you have a molecule of weird size or shape, it obviously is going to influence how the molecules flow to a greater or lesser degree, depending on that shape and how symmetrical or unsymmetrical it is. And intermolecular forces also have a major role in this, because, well, intermolecular forces measure how strongly individual molecules are attracted to one another. So all of these are contributions or factors when we look at the viscosity of a liquid. So that's all I wanted to say about liquids. So now I wanted to talk about solids. So solids come in two different forms. We have a crystalline solid, and we have what's known as an amorphous. We could say that crystalline is ordered, and we could say that amorphous is random. And so what I mean is, let's actually make some circles. So when we have a crystalline type of solid, we have this nice ordered structure over here. Whereas when we have an amorphous solid, we're going to have some random structure that's just going to have these molecules just clumped together in random orders. So this would be an amorphous, and would be a crystalline. So how should I put this? Usually crystalline structures are more difficult, or they definitely are actually more difficult to achieve, because crystalline structures will require a more precise, how should I put this, procedure in which they are formed. For instance, let us look at silicon dioxide. Silicon dioxide is something that we are all familiar with, and it is typically known as glass. Or that is one of the names that it has. It has a bunch of names, but we typically mostly know of it as glass. When we look at the crystalline structure of silicon dioxide, we will typically refer to it as quartz. While the amorphous structure is known typically as glass. So rather than putting glass here, let's just put this right here. So although we have the same exact molecule right here, the arrangement of how this molecule essentially comes in a full structure is going to determine how it behaves in its solid state. And this is between the crystalline and the amorphous forms. Now, glass, pretty much all glass that we associate with is in this amorphous state. All the glass that we have in our windshields for our cars, our windows, our computer screens, everything that we pretty much use that has glass in it is pretty much glass in this amorphous state. Glass in this crystalline state, which is quartz, is much more difficult to achieve. The process in order to get glass in a crystalline state requires a very slow cooling of the glass, which will allow the individual silicon dioxide molecules to fall nicely into place to form this ordered structure. Where when we cool things at a more rapid pace, we get the amorphous form because things just need to settle where they are. And as a result, they don't get to essentially sit in the nicest of ways. Quartz has some very unique properties that glass does not have, such as it typically will have a higher melting point than glass, because this ordered structure allows it to essentially form stronger bonds with one another. Each individual silicon dioxide molecule is equally dispersed and distributed with its bonds to every other silicon dioxide molecule. While in the amorphous state, we have the silicon dioxide molecules essentially just spread everywhere. No real pattern going on, and as a result, we have uneven sharing, and as a result of that, we have a structure which is less sound. So another unique property of it is its ability to transmit light. We know that, well, we all know that glass is transparent and light can pass through it. But typically in the chemistry fields, when we do experiments with ultraviolet light and pretty much light that has very high frequencies with very tiny wavelengths, we need to use quartz materials to pass the light through, because this amorphous form of glass will actually absorb the light as it passes through it, and it'll mess our results up. This crystalline form of glass will not absorb the light that passes through it. And part of the reason for this is because the energy that these individual silicon dioxide molecules have is lower, and as a result, it requires a greater amount of energy to actually excite them. So they're not going to absorb that energy. Where in the amorphous state, these molecules have a slightly higher energy, and as a result, they're more easily excitable. And the reason that they're in a higher energy state is, well, in the same way when we talked about bonding, how bonding lowers the energy or the overall energy of the two elements that or two or more elements we combine to create a molecule. By creating this crystalline structure, we are further stabilizing the molecule, where in this amorphous structure, we have a bit of randomness, and some molecules may be stabilized more so than others, and as a result, we have not as stable of a structure as this crystalline structure. Another thing about crystalline structures is, unlike glass, you can't really create crystalline structures in the shapes that you can with glass. For instance, all the neat thing like artwork that you do with glass, with the glass blowing and the twisting of the glass and the mixing of it with different colors, none of that could be done and create a crystalline glass. And the reason is because that glass, as we are blowing it and twisting it, well, we are completely warping the individual structure of the individual silicon dioxide molecules. And we are also cooling the glass as we are working it. And as a result, the molecules can't really set into place in this nice crystalline form. And so it takes on this amorphous form. In order to get a crystalline piece of glass, it usually has to be machined. You either have to find or grow a large piece of quartz crystal, and then using different methods, cut the crystal and polish it into the shape that you want. This is the primary reason why quartz is so much more expensive than glass. Even though it's the exact same molecule, the process of making quartz and shaping it into the structure we need and we use is just so much more involved than the process of making glass. So take that in mind, I guess, if you ever look at things, if you're interested in, for instance, buying quartz, because if you see a price that's really low for quartz, it probably isn't quartz, because the process of making quartz is incredibly difficult. Also, if you see quartz in very fancy, smooth, and twisty shapes, there's a very, very high chance that it is definitely not quartz, because as I said, that's not really possible. You have to machine the piece of quartz into the shape that you want. So you can't really bend and twist and blow it like you do traditional glass. So let's see. With these two different states, these crystalline and this amorphous state, we actually have several new types of things, or not really new, or 4 new types of things that I wanted to talk about. And these are the types of solids. So right here, what we were talking about was the structure of solids. So let me move this a little bit. Let's call this structure. Now, the types of solids, there are 4 types, and you are familiar with just about every single one of them because we've talked about them at some point in this lesson. Those 4 types are the ionic type, which you all are familiar with. We have the metallic, which I briefly mentioned. We have this new type of solid, which you have not heard of before, or you may have heard of before, but you probably haven't, which is known as a covalent network. And then we have a molecular solid. So here are the three types of solids that we have. We could say let's first describe the attraction between the individual atoms. So when we talk about ionic solids, well, the attraction type is ionic bonding. So because ionic solids like NaCl are essentially, as we talked about, just chains of sodium and chloride just strung together in these block formations that we will talk about again in a moment. I know I mentioned it a few weeks ago. The next type is metallic, and the metallic or the forces that are holding these metallic compounds together are known as, again, metallic bonds. So nothing new. Covalent network, the forces that are holding the covalent network together, as it's in the name, covalent bonds. And the forces that are holding these molecular solids together are the intermolecular forces. I don't want to do that. Let's see, what else do I want to say? So an example of an ionic solid would be something like NaCl, MgCl2, let's see, Ag or Al2O3. So these are all examples of ionic solids. Metallic solids are very simple in describing them. They are essentially just a metal. So something like copper, something like iron, something like tin, lead. Pretty much if we have a clump of this metal, we have a metallic bond. These covalent network compounds are the new type of structure that we talked about. And I should note, that the covalent network is essentially something like, well, glass, like silicon dioxide. Another type of covalent network is something like diamond. That's all I really want to say. There's not too many covalent network compounds that come necessarily to mind. They are a very interesting type of compound because unlike a molecule, or not a molecular, really, unlike a molecular compound or a molecule. So we say we have the silicon dioxide right here, for instance. So we have silicon, and it's going to have two oxygens coming off of it as such. And so silicon dioxide is actually going to have a charge on it if we pretty much keep it as it is. So because of this, we are going to see silicon form this network. Let me move this. Actually, do I have a picture of this maybe? So we're essentially creating this network structure with the silicon and its two oxygens. Let's see, do I want to draw any more? That's pretty much all I want to draw here. You're saying that the silicon are essential. Why is you doing this, Microsoft? All right. So in the covalent network, unlike the molecular compounds, these molecules form these giant chain-like structures with one another. So when we talk about silicon dioxide, although we can look at silicon dioxide as the single SiO2 molecule, which is Si and two oxygen coming off of it, this molecule is actually going to form a covalent network with other silicon dioxide. And that's how we have glass. And that is the reason why when we take glass, glass is such a strong compound. When we think about it, all of the structures that we essentially have that form large pieces of things are some form of polymer, some form of metallic compound, or some form of covalent network. For instance, all the metal that we have are essentially metallic bonds that are essentially forming with one another. And these metallic bonds are this bond that allows individual pieces of metal or metal atoms to essentially stick to one another to form giant sheets. When we have a covalent network of things, we are also forming these giant sheets of things. When we look at a molecular solid, though, for instance, we have molecular forces that are being involved here. And these molecular, hold on one second, I'm going to disable this express keys. All right. So when we talk about molecular solids, instead of having this network that we have in all of these others, because essentially in every one of these others, in the ionic bonding, the metallic bonding, and the covalent network, we have this network of structure. We have this structure that sort of makes it hard to define an individual piece of the entire whole. For instance, in a covalent network, we have these silicon dioxides bonded to each other in this repeating pattern that is just continuously repeated. And so it's sort of hard to essentially discriminate any individual silicon dioxide molecule. When we look at a metallic compound, again, it's just sheets of or repeating spheres of the metal, one after another, just making this piece of material larger and larger and larger. When we have this ionic compound, we essentially have, well, we have these crystal lattice type structures that the compounds essentially form. And again, there's no individual NaCl, no individual MgCl2. They're all just bonded together repeatedly, continuously throughout. Finally, when we look at the intermolecular or the molecular structures, they are the only ones that are a little bit different from the others. And that is because, well, they are discrete from one another. There's no sort of repeating pattern to them. They are essentially an individual unit. So examples would be things like H2O. Let's see, CO2. Let's see. H2SO4. So these are all examples of molecular compounds. Very interesting to say the least, because did you guys have a lab where you crystallize something? So usually, if you're crystallizing something in one of the labs, you're usually either crystallizing this molecular compound or an ionic compound. So either your molecular or ionic compound will be dissolved in solution, and then you will let it sit. And you usually want to cool your liquid very slowly, and it'll result in a nicer crystal formation. So as we slowly cool, we're going to allow this ionic compound or this molecular compound to essentially stack up on one another. With the molecular compounds, we're going to have essentially sort of just some structure like this, and then they're just going to stack on top of each other, and we're going to see intermolecular forces between the individual portions of the individual compounds. So unlike when we have our covalent network, metallic and ionic, which forms these this sort of structure that connects everything together with a very strong bond, this molecular solid right here is essentially very weak. It's very, very, very weak, as you would expect, because things like, for instance, medicine pills. It's very, very easy to take a pill that you get from the drugstore and grind it into a powder. And that's because the molecular forces that are carrying on between the individual molecules in that pill are nowhere near as strong as the covalent network that we would see or the metallic network that we would see. The ionic network can be very strong, but it's not always very strong. But most medicines that we consume are a molecule that has molecular forces which form a molecular solid. So when we look at all of these structures, these four types, all four of these types, when we are forming a solid, can actually go under the guise or the structure of a crystalline or an amorphous type of order. So we could have an ionic type of solid that is crystalline or amorphous, metallic, crystalline or amorphous, covalent network, crystalline or amorphous, and molecular, crystalline or amorphous, although molecular can't really create much of a crystalline structure per se. It is highly dependent on the structure of the individual molecules in this molecular compound, but usually we don't see as elaborate of a crystalline structure as we would see in these other three. So all of these four types of solids are the four primary ways in which a compound will form or come together and form a solid. And these four ways are essentially broken down into a crystalline and an amorphous form. So now that I've stated that, I want to essentially get back to what we talked about. I think it was, what chapter was it? I think it was maybe 2 sections ago. I want to talk about lattice structure again. And lattice structures have what are known as unit cells. Actually, before I do this, lattice structures are present in, let's see, I'm going to say ionic solids. And what else? Metals. So we have this lattice structure present in ionic structures and metallic structures. And I mentioned lattice structures before. And lattice structures describe the orientation in which molecules are essentially, or atoms of the individual elements, will pack themselves together to form a crystal structure. So the first thing, let's actually draw something. Take this box. Let's take this box and put it right there. All right. So let's take this box, duplicate it a bunch of times. All right, should be good. Let's go to our red pen. All right, back to my white pen. So we have this, what is known as a unit cell. And these red dots are known as lattice points. So I could actually So right here we have our nice square box structure. We could actually I'll extend this even further, can't I? Let's put this, send it back. Front. Front. All right. Looks a little bit funky. It looks like I have an extra box in there for some reason. There's something off scale, which is making things look funky. All right, we won't extend that any further. Hold on, let me. I'm drawing boxes. That's good. I don't know why I'm getting this weird box shape. Whatever. Let's try it out. So we're gonna put a cube there. There's a sphere there. All right. So the unit cell is essentially just repeating itself on this structure again and again. And we will call the lattice points essentially the points where the molecules reside, or the atoms. The other thing we need to know is the coordination number. Which is the number of lattice points each lattice point touches. So I don't know why the software acts so buggy. We take this, what do I want to look at specifically? So let's look at that lattice point right there. Let me change myself to a red marker, or a blue marker rather. That's way too thick of a marker. And we could actually look and see how many other points this lattice is coming into contact with. So we could see that this lattice is coming into contact with 6 points. 1, 2, 3, 4, 5, and 6. Let's make these green. So here is our 6 lattice points. And what this type of lattice structure is known as, it is known as a simple cubic lattice structure. And it has a coordination number of 6. Now let me do one more thing. Take this. So how would this structure look? Well, let's take a sphere. Let's make it about yay big. Let's take another sphere. Give it a little bit of 3D-ness. And let's use this brown pencil. We will say that this sphere represents one of our atoms. Let's call this some metal. Let's say this is copper. Yeah, that'll be a nice size. So we'll put one there. One there. Put one there. Put one there. We'll put one there. So at this point, we have our simple cubic structure right here. And I want to make a note of something. If we were to take this and we were to essentially cut along the lines of this cube right here, we would essentially have something occur. Let's see, I don't think I'm going to be able to draw this though. Pretty much. Maybe I will be able to draw this. What else? Essentially what's going on is each of these individual spheres are getting a portion of them essentially being chopped off. And specifically the portion that's being chopped off is an eighth. So each of these spheres are 1/8 of what they actually are. So how will I be able to draw this? Let's do a line like this, a line like this, a line like this. That should be good. Let's do this line like this, line. It's not really conveying how this should look. Yeah, I can't really draw this in 3D, but you guys do see what I'm trying to get at though right here, how if we look at the individual corners of this unit right here, and we look at the individual spheres, we're essentially going to chop off a portion of the sphere. Let's see, maybe I could. Desktop. Fresh. There we go. We see that we have our lattice points and we have our spheres that are essentially being rounded off on the edges. And so if we look at only this block right here, this cube, we could say, well, if there's 1/8 of a atom here, and there's 1/8 here, 1/8 here, 1/8 here, 1/8 here, 1/8 here, 1/8 here, and 1/8 here. Well, 1/8 times 8 is 1. So we have 8 corners. So 8 times 1/8 equals 1. So a simple cubic lattice here. Simple cubic coordination number. How should I put this? I don't want to call this packing. Does this have a specific? I don't think this has a specific term. Let's call this packing. So the packing is 1 atom per. So if we have multiple ones of these unit cells put together, and the unit cell is of a simple cubic type, each unit cell is only composed of a single atom. Therefore, if we know how many unit cells we have, we know how many atoms total we have, because we know that each unit cell, although has 8 atoms participating in it, there is only a total of 1 atom of space being occupied. Does that make sense? And there's nothing on the inside of the cube. I sort of just blew it up. All the spheres would be touching each other. They would be sort of packed right next to one another. All right. So the next type of unit cell is the 8th, because the 8th of the atom is the inside of the cell. Yeah. So the 8th of the atom or the 8th of the sphere occupies the inside of the cell. So if we have 8 spheres, and of those 8 spheres, only an 1/8 of them occupy the inside of the cell, that means the entire cell is only accounting for a single sphere, because we'll take those 8 portions and we'll recombine those 8 portions together and create 1 sphere. So the next type of unit cell is the body-centered cubic. And so the body-centered cubic, very, very, very similar to our simple cubic. What did I just grab? So here is our unit cell, and the difference for our body-centered cubic is it has 1 more lattice point, and that lattice point is in the center. So that's what I broke. That there. Let me take this. I don't know how this software is so janky. And so the difference with this one is, I'm just not gonna let me select this for some reason. And it's just refusing to let me select things now. That's not what I want to do. the software. So we're just only going to, for the body-centered cubic, is we are going to add it's like as soon as you start drawing anything on here, it starts to like lag and turn into this absolute mess. Let's see how far we can get before completely. So I'll put that right there. Let me push it backwards, order, send backward, put it all the way to the back. So we have a sphere in the center this time, and I'm probably going to stop drawing at this point because it's going to start to get very, very messy. And then finally, we have the last one. I'm not going to draw this next one. I'm just going to draw the unit cell for it. I don't think I can draw this successfully. Yeah, it's right there, I guess. Right there, right there, right there. This is known as, oh, you just don't want to change my pen, as the face-centered cubic. So the face-centered cubic obviously has lattice points on the face. And the body-centered cubic has a lattice point in the center. All right, just a few more things I want to talk about this, and then we'll go to gases. Let's see. We need to know coordination number. And the packing. Let's look at coordination number. And packing. All right. So based on what we talked about, any of you guys know the coordination number for either of these? Well, do you guys remember what the coordination number was? It was how many lattices were touching how many other lattices. So for this body-centered cubic, how many lattices are essentially touching each other? How many lattice points? We know we have one in each corner, and then we have one in the center. You're close. No, went too far. The coordination number 4, a body-centered cubic, is 8. Because you could always just look at this center one, and we could see that this center guy, 1, 2, 3, 4, 5, 6, 7, 8. That center lattice point is coming into contact with all 8 of the corners, and by that, because this is a symmetrical structure, every one of these corners come into contact with 8 other lattice points as well, because there are cubes around this cube. So the coordination number for a body-centered cubic is 8. How about the packing for this one? How would you think of that one? So in each of these cubes, how many atoms do you think we'll be able to fit? Nope. Remember how in the last one we could only fit a single atom in here? So how many atoms can we fit in this one? Yep, 2. And why can we fit only 2? Well, if we look at our last one, we were able to fit 1, and those were an eighth of an atom at each of the quadrants of this cube. And because the body-centered cubic only has a atom in the center, well, because that atom is in the center, that atom can't be cut off by any of the sides of the cube. So we're just going to add 1 extra atom to the total atoms, which make up the quadrants of this cube, or not the quadrants, the 8 corners. And that will give us a packing of 2. So with a body-centered cubic, we will be able to hold 2 atoms inside of this unit cell. The face-centered cubic is a bit more difficult to visualize. Does anyone have an idea of the coordination number for this guy? Any ideas? How many atoms are next to each lattice point? Whoa, way too much. Nope. It will be more than 6. It will be more than 8 because we know that simple cubic has a coordination number of 6. Body-centered cubic has a coordination number of 8, and face-centered cubic, well, we only added more lattice points, so it has to only have more, a greater coordination number. It's much more difficult to see this this one than the others because, well, let me see if I could actually, because we have a point, a point, a point, a point, and a point. And then we're going to go up a level, and then on top of the next level, we're going to have a point, a point, a point, and a point. And then we're going to go up a level, and then we're going to have essentially this pattern again right here. But we also have to take into account that, well, every single one of these is essentially going to have things next to it as well. So let me say this one. This is bottom. This is top. So let's look at let's look at this center atom right here and see how many atoms are next to it. Well, we have 4 right here, right? This top portion would be the it would be the top of the cube right here. So that's what this would be. This right here would be the side of the cube. So let's see if I can draw this. So we sort of have a dot there, we have like a dot there, we have a dot there, we have a dot here. So essentially there's going to be a red dot there, a red dot there. I'm not going to do that. It's going to get really, really sloppy. But maybe you can sort of deduce how many points each of these are next to already. So if we look at this, let me zoom in a wee bit. If we look at this point right here, it's next to 4 atoms, right? And this cube, this surface cube, has atoms underneath it and on top of it. And the atoms underneath it have the same exact pattern as these atoms on top of them. So these 4 atoms are underneath these 5 atoms, but this center atom is touching all of these. This center atom is then also touching all of these on the bottom, and it's touching all of these on the top. So we can just add this together. We have 4, 4, and 4. So 4, 8, and 12. And so that gives us a coordination number of 12. So every single atom that is in a surface or a face in this not the body centered, in this face centered cubic pattern is going to have a coordination number of 12. You guys able to see how each of these lattice points are coming into contact with 12 other things? You guys hear me? It's really hard to draw it. If I had spheres and you were able to play with a model in front of you, you'd be able to see it. But it's really hard to show it. Let me see if there's any images. I can't really find any images like it. Yeah, and all of the other images I have here only make this look more complicated. If you can't see it, don't worry too much about it right now. Not too big of a deal. Just know that a face-centered cubic structure will have 12 points of contact. How about packing? Anyone have any idea how many atoms will fit into one of these structures? We know that a simple cubic has one. So that means the face-centered cubic has to have at least one, because each of these four corners accounts for 1/8 of an atom, or 1/8 of a lattice point. And so 8 points together make one total molecule or unit. And so we also have these sides. So we have 1, 2, 3, 4, 5, 6. We have 6 sides. Exactly. The answer is 4. So those 6 sides each have half an atom, and if we take those into account, we essentially get 4 atoms. So I really want to talk about for the solid state of matter, I believe. Just wanted you to understand the lattice structures and whatnot. I'm not going to go into I'm not going to go any more into detail into this. I think it's not really relevant for anything you guys need to know. So let us move on now into the gaseous state of matter. Geez, why won't my mouse select this? So let's call this gas. So everything I've talked about so far today was mostly all conceptual. More or less, there's not going to be much work for you to do in pretty much everything I just talked about today. Or not everything I talked about today. We're about to do a bunch of stuff with problems, but pretty much everything I've talked about is for the solid state of matter and the liquid state of matter, viscosity and surface tension. And did I actually finish talking about those? No, I only talked about viscosity. So to finish talking about this very, very quickly, capillary forces are what happens when we have a very thin tube and we have a substance in the tube. We have what are known as adhesion forces. Between liquid and tube. And we have cohesive forces between liquid and liquid. So keep that in mind. The difference between the word cohesion and adhesion have to do with what the individual things are connecting to. So when we talk about adhesion, you could think about adhesive, like glue or tape. So when we have adhesive forces, those are forces that are between two separate entities. So usually the glue in whatever you're gluing your thing to, or for instance, if you ever put water into a test tube, you will see that, for instance, or water into anything made of glass for that matter, you'll notice that water likes to stick to glass actually very nicely. And it is because glass actually is slightly polar. And because of that slight polarity of the glass, the water sticks to the glass. This is why water forms the way it does. Now, I want to talk about this really quick, the meniscus. So let's say this is a glass test tube in both cases. Well, let's say I have mercury in here and I have water in here. So mercury and water. They form a different type of meniscus. Mercury is not polar, and as a result, it does not stick to glass. If you've ever broken a thermometer, you'll notice that the mercury just slides right out of it if you've ever actually got in contact with a mercury thermometer. And that is because mercury is non-polar and the glass is polar, so they don't want to stick to one another. As a result, mercury inside a test tube, the primary force that's going on is mostly only cohesion forces between mercury and itself. While when we look at water inside this glass tube, we have both cohesion and adhesion forces at play. The cohesive forces are holding together the water to one another, and the adhesion forces are holding the water to the surrounding. And these two forces are essentially describing how these fluids are behaving inside the tube. When we look at capillary effects or capillary forces take place when we have cohesive forces and adhesive forces at play. And we will see that the liquid will essentially climb the tube. And it has to do partially with a pressure differential and partially with the forces that the liquid has, the adhesion forces that are going on between the liquid and the glass. And in a way, because the test tube is so small, the adhesion forces now have a major strength. Because there's such a small amount of liquid, the adhesive forces don't really need to use so much energy to adhere the liquid to the other material. And as a result, the liquid can somewhat climb the material. And that's what we see when we have capillary effects. The liquid will essentially flow through the tube because it's not being restricted by any sort of, how should I say this, any sort of forces, or rather, it's not being restricted to a great enough degree. And because the capillary forces are currently essentially only occur in very small or thin-walled vessels, such as capillary tubes or capillary type vessels, it's because there's such a small amount of the material or the liquid in play. And so the forces that are taking place outside of the liquid, the adhesive forces, are allowing the liquid to essentially climb up the vessel with more vigor than you would normally see if you had a large amount of the fluid. Because if you had a large amount of the fluid, well, the capillary forces, or rather the adhesive forces, wouldn't be strong enough to essentially move that liquid up the walls of the glass. Does that make sense? Again, this was just more comprehension type stuff. you probably won't see any questions like this, or at least any questions directly related to this on the quiz or exam. More conceptual, and it's useful for a few other things that we will talk about shortly. So gas. Gas is our third state of matter. Hold on one moment. So what is a gas? Well, when we talk about gas, we have to talk about something called pressure. And pressure is essentially the force exerted by a gas. So a gas is a phase that a material could enter. And in this phase, the material is behaving in a much different sort of manner than the liquid or solid state. It is moving with a much greater freedom than you would normally expect to see a material move at. There is very little resistance between the individual elements or molecules or atoms in the gas. And so the individual elements or molecules or atoms are able to move around quite vigorously. So if we had a container, and we had a gas inside, we could just imagine the gas as a bunch of little spheres essentially bouncing around inside there, smacking against the wall of the container very furiously. As we raise the temperature of the gas, we are going to cause the gas molecules inside this container to move around with a greater speed. And as a result, they are going to hit the walls of the container with a greater force. That greater force will in turn cause an increase in pressure. So let's talk about a few ways we can define pressure. We will define pressure as a force divided by some area, because we want to know how much area that force is acting on. Because if we had a very, very, very large force over a very, very, very tiny area, that wouldn't necessarily be that great. But if we had a very large force over a very great area, that possibly would be a very great force. So let's see. Let's give you guys units of pressure. So we have pascals. I know I'm going to spell this wrong. All right. So we have Pascal. We have bar. And we have millimeters of or inches of mercury. We also have PSI, but we probably won't use PSI for many things. Oh, we have torr as well. And atmospheres. So these are all different units we could measure pressure in, and you've probably heard of some, if not all of these before. So 1 atmosphere is equivalent to 1 atmosphere, or also 760 millimeters of mercury. Let's see. Torr is 760 torr. Let's use millimeters. So that's 760 millimeters. Let's see, what else? Pascals, we have 1001. Three, 2, 5. PSI, we have 14.7. And this, the last one is bar. Where is it? It is 0.980. 1.013, that's what it is. 0.013. I think that is all I need to give you. All right, yeah, that's all right. All right. So these are the different units that the pressure is traditionally measured in. So here we have all of them. Pascals, I should probably give you the units. Is millimeters of Hg. Pounds. So lb per square inch. So inches squared. So torr is torr, atmospheres is atmospheres, bar is bar, and pascals is pascals. So these are the several primary units that we will essentially be looking at or using when we talk about gases. And I would recommend that you guys become familiar with all of these terms. Whenever you see any of these terms, you should immediately associate it with gas. So to go over this, you know what they are: Pascal, bar, millimeters of mercury. PSI stands for pounds per square inch. Torr, and ATM, which stands for atmospheres. And obviously, atmospheres is a measure of how we are on Earth. And every one of these units are in atmospheres. So pretty much 1 atmosphere is 760 torr, 14.7 pounds per inch, 760 millimeters of mercury, 1.013 bars, and 1,325 pascals. So when we talk about gas, we are going to need to define a bunch of terms right here. So let us do that. So P is pressure. We have V is volume. N is the number of moles. And T is the temperature. And I need to make you guys aware that this temperature has to be in Kelvin. So make sure that we always use Kelvin for these unless specified otherwise. The other thing we need to know is we need to know this ideal gas constant, which is designated as R, and it has the value of 0.08206 liters multiplied by atmospheres divided by moles multiplied by Kelvin. So make sure if you use this constant that you have the proper units, because I'm going to give you another constant. Here is another R. This R equals 8.314 gram joules per mole per Kelvin. So make sure when you're using these terms that you have the correct units that be associated with them. These terms represent the same thing, but the units are different. So we've messed around with the numbers to use different units to cancel out different things depending on what equation that we are going to play with. So just keep that in mind. So. I'm just not going to switch my pen. All right, so we will start with what is known as the combined gas law. So the combined gas law states the following, that if we take the pressure and then we take the volume and divide it by the number of moles along with the temperature, and then let's say we take a new pressure, a new volume, a new number of moles, and a new temperature, and we equate these two terms together, we will see that we essentially are going to end up with something like this. The ratio, here is what we need to take note here. The ratio of the pressure, volume, moles, and temperature will always equivalent or come to some constant, and that's what you guys need to note. all of these factors here play together, change one feature of one another or more. And so, for instance, if we increase the temperature of a gas, you would expect the pressure to increase or the volume to increase. If we increase the number of moles of a gas, we would expect the pressure to increase, the volume to increase. But we'll go all over all this. But we should note that when we take all of these values into account, that they will form a ratio, and this will essentially allow you to equate any two gases to one another if you have their pressure, volume, number of moles, and temperature. Does that make sense? So, using this combined gas law, we are going to talk about a bunch of different laws here. And the first law that we are going to talk about is known as Boyle's law. So Boyle's law is stating, or rather not stating, asking what would happen to a gas if we kept the number of moles and the temperatures constant. So we're going to take the moles and we're going to take the temperature and we are going to hold constant. So let's look what would happen. Let's take our ideal gas equation. Actually, we could take our ideal gas equation just like that. And I'm saying that we are going to hold moles and temperature constant. Therefore, because they're being held constant, they're going to be the same. And therefore, we can just cancel them completely out. And with this information, Boyle's law states the following: that if we hold the moles and temperature of any gas constant, if we have the pressure and the volume of the gas initially, we could determine the pressure and the volume of the gas as we change those two factors. So let's actually look what this plot will look like. So I have a Cartesian plane right here. And so let's call the y-axis pressure, and let's call the x-axis volume. So we will see a graph that looks similar to this. That as we decrease the pressure of a system, or rather, for instance, as we increase the pressure, the volume will increase. So how should I put this? So as volume increases, pressure decreases. And we can see that, and that sort of makes sense. As we sort of take the volume of a space and we increase the space of that volume, but we don't allow any gas to come inside. We are just simply going to expand the space. We are going to decrease the pressure in that space. And in the same way, if we decrease the volume of a space, we are going to raise the pressure in that space. Makes sense? So this is essentially what Boyle's law is stating. And so more volume equals less frequent collisions and as a result, less pressure. And so as volume increases, pressure decreases. And as pressure decreases, volume increases. So the next law that we will talk about is known as the Gay-Lussac's law. So and so what this law says is that if we hold volume and let's see, moles constant, what will we get? So we pull that initial equation down here. So instead of temperature this time, we are going to cross out volume because we're holding volume and moles constant. And so we will get the following equation. Over T1 equals P2 over T2. So this is the equation for the Gay-Lussac's law. And so we would have a graph that looks like this. So let's say that pressure is going to be on the left and temperature is going to be on the right. Use the same ink. No, I didn't. There we go. So we see that in this law that as the pressure goes up, the temperature goes up. So pressure is increasing and temperature is increasing. Pressure decreases, temperature decreases. And so that also makes sense when I first was talking about gases, because let's say that we have two boxes. And let's say this one's at 300 Kelvin and this one's at 1000 Kelvin. essentially what's going on is these molecules inside the box that has the higher temperature are going to be moving around a lot faster. And because they are moving around a lot faster, they are going to impact the walls of the box with a greater force. That greater force means it's going to hit the walls with a greater pressure. And so a greater pressure will be experienced as we increase the temperature. And in the same way, as we increase the pressure on a gas, we will also increase its temperature, because as we push a gas and try to compress it more and more, it's essentially going to increase those amounts of impacts. And that's going to generate friction, which creates heat. So as temperature goes up, pressure goes up. So we could say as temperature goes up, pressure also goes up. That is what the Gay-Lussac's law says. So the next one, Charles' law. So Charles' law is essentially talking about a relationship between temperature and volume. And so we are going to hold pressure and moles constant. So we are going to hold pressure, and we are going to hold the number of moles constant. So these are being held constant. So let's take this equation. Oh Lord, it's just not letting me select, and now I just closed it somehow. So this time we are going to cross out pressure. This will leave us with the following equation. The volume over the temperature equals the volume over the temperature. I'm going to use capital T because little t is usually time. If we graph out this equation, we will see essentially a plot very, very similar to the last one. This is a little more difficult to explain than the previous ones. And as we could see, if we have volume here and temperature here, if we increase the volume, we are going to increase the temperature. And if we decrease the volume, we are going to decrease the temperature. So let me try to draw it as such. So this is essentially a matter of external versus internal pressure. And so we could imagine if we had a balloon and we filled it with a gas. As you see that as we increase the temperature of that balloon, the molecules inside that balloon are obviously going to increase in speed. But because we do not have a balloon, or because we have a balloon rather than a solid box, the balloon is able to expand. And so as we increase the temperature of the gas inside that balloon, the balloon is actually going to expand and the volume is going to get larger. And so this is where we get this graph from. And as you see, as we increase the volume of the balloon, we will increase the temperature inside the balloon. That makes sense. All righty. We have one more law left, and then we have, maybe I'll turn this into 2 lectures, because this is actually getting really long. All right, let's finish up these laws, and let's see how long have I gone. 2.5 hours so far. I'm going to finish these laws up, and then we will meet one more time, I think, this week to finish this off. It'll be really, really quick to finish this off. So let's see. The next law is Avogadro's law. So Avogadro's law is the relationship between volumes and moles. And so we are going to hold the pressure and the temperature constant. So just not going to let me select this for some reason. So if we hold the pressure and the temperature constant, we will cross out pressure and temperature, and we will get a new equation, which is V over N equals V over N. And we will get an equation that looks sort of like this. Nope, still blue. It just does not want to change color. Alright, so this is going to be the number of moles, and this is going to be volume. So right here we say as the number of moles increases, the volumes increase, and as the volume increases, the number of moles have to increase. And this only makes sense because as we add more stuff to some amount of space, we are going to fill that space and require more volume. Avogadro's law is the most basic, I think, and pretty much states what we all pretty much know. As we put more stuff in, we are going to require more room to hold that stuff. So that is Avogadro's law. So this is pretty much all of the laws. The next portion, we would be going over a bunch of problems. But since we've been together for about 2.5 hours almost now, would you prefer to meet again this week to finish this topic up? Let's see. How's tomorrow? Are you guys free on tomorrow on Tuesday? or Wednesday. I don't want to push it to Thursday because you have an exam on Thursday. So I'd prefer Tuesday or Wednesday, or exam on Friday rather. So I'd prefer Tuesday or Wednesday. Tuesday or Wednesday at around 3:30, 4 o'clock.